In the Friday's folder, the 15th, I put a couple sets of practice problems. One dealing with writing the initiation, propagation, termination steps of the alkyl halide, and another problem set with writing the products of different bromination, chlorination at the different temperatures. And they both have narrated answer keys, so they're there for you to use. I guess chapter 15 is due today, and then chapter 18 in Top Hat's due on Friday. Okay, so I put those dates in. And even though it said that the Top Hat for 15 was due a few minutes ago, if you get it today, the deadline is basically today. Okay. So today's sort of topic is looking at allylic, finishing up one important thing on allylic radicals, as well as looking at allylic carbocations, and then looking at 1,2 and 1,4 addition. So if anybody looked at this, do they have any questions? Well, there's one thing I want to finish, and that is the issue of our selectivities of looking at an allylic system. So if you have an allylic system and you're going to do bromination with light or with heat, what we would say is that the special position here, this most selective position, is going to be the allylic position. So that's where the bromine's going to go. And it's on par with the 1700 to 1 that we had for a tertiary halide. So when you brominate an allylic position, that's where the bromine should go. And when you brominate an alkyl benzene, if you do the same thing there with bromine, light, or heat, you're going to brominate exclusively at the benzylic position, which is an analogous position to being allylic. So that means you're going to end up with the bromine in the benzylic position. Now, this for benzylic is true, okay, because bromine will not react with an aromatic ring. But is this reaction right here, is that reaction true? What if I would have written that reaction? What if I would have written that reaction with just what if I just would have written it like this? And I would have left off the light or the heat. What would be the product of that reaction? Jacob.
Well, there wouldn't be a reaction because there's nothing, no energy going into the reaction.
No, there would be a reaction. There is going to be a reaction, Carolyn.
Two BRs added to the
So I'm going to get Br addition to the double bond. So I'm going to end up with adding 2 Brs. They're going to add, there's not Markovnikov or anti-Markovnikov, and they would add 100% trans. So I would get Br2 addition. And so the problem is that when we're trying to do free radical halogenation at the allylic position, just because I say, well, I'm going to add light or heat to that system doesn't change the fact that the bromine is going to add to the double bond first. So you're going to get this product actually, or actually, no, you're going to get this. This is going to be the product, and this one will not form because the bromine is going to add to the double bond much faster than do a free radical halogenation. So whether the light or the heat is there is irrelevant. When you have a double bond, it will add, the bromine will add. So on Friday when I did this reaction, I probably said, later I'm going to show you that this doesn't work, and it's later. So we can't do bromination on an allylic position with Br2. Now we can with the benzene ring, because we'll find out later benzene rings don't react with bromine. They're too stable. So with this molecule then, what we end up doing is we end up having to go back and use a slightly different reagent. Okay. And so the reagent that we would use is not bromine and light, because bromine and light, as we just saw, does not produce that. Instead, we're going to use what's called NBS, which is N-bromosuccinimide. So this reagent, the N-bromosuccinimide, will actually produce Br dot. It will produce bromine atoms when it's heated. But it will not produce molecular bromine, which would then add to the double bond. So this is simply a source of a Br dot, not Br2. And so we can use this NBS as our free radical halogenating agent. And we can use this for anything. We could use this for an alkane, we could use it for an allylic system, we can use it for a benzylic system. It doesn't matter. Okay. So if I wanted to do this reaction up here, I should not use bromine and light. Instead, I should just use NBS. And then that would give me the allylic bromide.
But you still need to even.
Yeah, this reaction involves the NBS. The NBS requires a little bit of heat to it, but it's not. So what we can't really do with the NBS is we can't do the low temperature, high temperature stuff that we can with free radical halogenation. So the free radical halogenation at less than, or with light room temperature versus greater than 300 degrees Celsius, that has to be done with Br2 and alkanes. It can't be done with these allylic systems. Nor would we try, because for the allylic system, it just has that preferential place where the bromine is going to go. But you could, in a bind, if you forget the bromine, you could use NBS to do free radical halogenation on an alkane. But normally it's used with allylic systems. Bless you. Okay, so that's sort of a loose end from Friday, that if you've already finished off your chapter 15, you saw that you can't use Br2 and a double bond. They're incompatible. All right. Okay, everybody okay with that? I'll take that as a yes, since I see no heads moving one way or another. And I hear nobody saying, hey, what about this? Okay. Okay, so I have all the pictures from the... But what I want to do is... Okay. I should ask how many people looked at the video for today and then turn my back. All right. Let's do this. Let's talk about allylic carbocations, because that's where the fun is. And we need to talk about we need to talk about allylic carbocations because we're going to build ourselves up to reacting benzene rings. So let's say that I give you this reaction. Tell me the first step. Lexi? The leaving group leaves. We agree? Okay, I do. I guess. Okay. That's the first step. Now, why did the leaving group leave? Why didn't the water attack? Carolyn? Okay. What makes this reaction SN1 though?
It would be a weak nucleophile and a secondary carbocation.
Well, secondary halide. So this is a weak nucleophile plus a secondary halide, so that's going to force the reaction to go SN1. And if it forces it to go SN1, then that means that it's automatically going to lose the halide. Right? The water can only react with the carbocation. So far so good. Now, this allylic carbocation, does it have a resonance structure? Yes. So let's write it. So if I write the resonance structure for that carbocation, it looks like this. Now, what's the real structure of that carbocation? Is it the top one, the bottom one?
It's a mixture of both.
It's a mixture of both. What would we call that? The resonance hybrid. So the true structure of this carbocation is the resonance hybrid. We know how to draw that? Maybe we need a review. Again, no heads bobbing one way or another. I guess I'll just make the decision. Let's do a quick review. So writing a resonance hybrid is like writing a transition state. It's going to be the average of the two. So what we do is we write all the single bonds in place. Then we average bonds and charges. So for this, we're going to have a partial double bond because we've got a double bond and a single bond. So double bond, single bond, average, partial, double bond. Single bond, double bond, partial, double bond. So we average charges first. Now let's average we can do bonds first. Now charges. Now in these systems, everywhere there's a positive charge in the resonance structure, there's going to be a delta positive in the hybrid. So I can just basically say delta positive here and a delta positive here. So this is my resonance hybrid. And that is the true structure of the carbocation intermediate. Question. Which of the two carbocation resonance structures is most stable? Your choice is, we're going to poll with hands. Your choice is A, B is more stable, or they both have the same stability. So how many say that A is more stable? B is more stable. Same stability. Okay, all I saw were A hands. Why is A the more stable one? Katie?
Secondary carbocation.
So it's a secondary allylic carbocation. I'm going to throw the allylic in. And B is only a primary allylic carbocation. If I just said B was a primary carbocation, we would expect it not to exist. But it's primary allylic, it can exist. So that's a secondary carbocation, secondary allylic. So it's going to be more stable. So this one's going to be more stable. Okay. All right. So far I'm writing the mechanism of this reaction. But this reaction now has a intermediate with a resonance structure. So I should be reacting the water with this resonance hybrid. But if I do that, I got to keep track of where the double bond goes. So why don't I just treat these two resonance structures as if they were the true intermediates? And let's react each one with water. Okay. So I'll just rewrite them down here. So here's the first one in resonance with this one. And so now let's react the H2O with this carbocation and write the final product. Now, remember, this is 2 steps. So to save some time, I'm just going to write the OH as the final product. And the same thing here, taking the water and reacting it with the primary allylic carbocation. That again is going to be a 2-step reaction to then give me that final product. Okay, so I'm simplifying. When I ask you to do this on a test or a homework problem, you are not allowed to say water, 2 steps, and then just put the OH. You got to bring in the water, make the oxonium ion, and lose the H+. Okay, but I'm just going to shorten things up here. Okay. So, intermediate A makes product A, intermediate B makes product B. So, when I did this reaction, because the intermediate has two resonance structures, I've made now two different products. So, here's my question. My question is, which one of those two products do you think is the major product? And you have A or B, or A and B are have equal percentage. Okay. And I will give you, using my fantastic new large timers, 1 minute to discuss. And then I'm going to call on the wheel of death to ask somebody what they think. I'm going to ask multiple people what they think. Okay, so discuss. Okay, your time is up. Now, it's going to be perfectly fair of me if somebody gives an answer to ask why. You probably pass on the why, and somebody else can give me a why. But I want to know both what your answer is, and ultimately we're going to need to know why. So, let's see.
Lucy Pelso.
Okay. I think it might be A because it has the more stable chromophene.
Okay.
Abby Bernard.
Yeah,
Same thing. Okay.
Caroline Maltese.
Also A. Because it can have a lower activation.
Okay. Could just go everybody.
Lauren Phillip.
Oh, we also said A.
Okay. Same reasoning? Okay. So did anybody choose B? Maddie, why'd you choose B?
Substitution pattern is on the bottom.
Lexi? Same reasoning? How many other people said B because of the substitution pattern? Pat? Okay. All right. So how many people said A? How many people said B? Okay. Now, I can't find any flaws in either of those two logics. Right? Because here is a reaction where we have two things that are competing against each other. Product A would come from the more stable intermediate, but product B would be the more stable product. Right? And if you're saying, well, wait, what about the alcohol part? Do we have any rules about primary, secondary, or tertiary alcohols being more stable? No, we don't. Do we have rules about more substituted double bonds being more stable? Yes. So we have these two things that are in opposition to each other. Okay? And I can kind of see why the people who wrote Top Hat decided to put free radical halogenation before this, because we were stuck with a similar dilemma last week, right? We had statistics versus the more stable intermediate. So we have a similar situation here. More stable intermediate versus more stable product. So which one wins?
It depends.
It depends. What were you going to say?
I was going to say it depends probably on heat, like before, because product A, when you look at the resonant hybrid, it has 3 hydrogens, where product the B in that has 2. So if we're doing statistics like that, we can. No.
I'm going to stop you right there. Statistics only applies to free radical halogenation. So we're not going to, that's the only time we use statistics. Here it's just pure intermediate versus product stability. And it will depend. Just like last time. What will it depend on? It will depend on the temperature of the reaction. It will also depend on the reaction time. Do I let this reaction go for 10 seconds or do I let it go for 10 hours or 10 days? So the major product is going to depend. It's going to depend on this. Okay. So I always like to do this when people haven't read ahead or haven't watched the video ahead, because then we kind of get that both products could be the major product just by thinking about what we know to this point. So, which is it? So let's go through the it depends argument. So I hate putting it in slideshow mode because then it draws indiscriminate lines. Okay. So there is a very nice diagram in the notes, in the PowerPoint notes, that I'm just going to reproduce here. And I'm going to start with the intermediate. I'm going to start with the intermediate in the middle here, with the resonance hybrid of the intermediate. And so what you have to realize is this, that we say the secondary carbocation is more stable. And what that will do is that will then produce a transition state that has a lower energy than the transition state for reacting water with the primary carbocation. Okay. So when we dice this resonance hybrid up into two structures, we say one's more stable than another, but really we have to react the hybrid. And so when we react the hybrid at the secondary position, we get a lower activation energy than we do at the primary position. Okay, so that's the first thing. That's the first diagram that we need to draw. Okay. Now, just looking at this, which reaction, and so this is plus water. Which reaction, the one on the left or the one on the right, do you expect to go faster? The one on the... Why? It's got lower activation energy. So we would expect the reaction to go to the right would be faster. And the reaction on the left would be slower. And there's nothing I can do to change that. Right? It's all about activation energy. So reacting water with the secondary carbocation is going to have a lower activation energy. But now let's remember what happens on the other side. When I react the secondary carbocation, I'm making the product that's less stable, whereas over here, I'm making the product that is more stable. That's not a bad diagram. Okay. So initially, I'm going to get more product, more right-hand product than I am left-hand product.
Reverse, because the one on the right, the one structure you just drew, that's the more stable one.
No, this is not. This is only a. This is like a terminal alkene versus this one being internal. So this reaction has opposite results. When you go through the lower transition state, you actually make the less stable product. If it made the more stable product, then there'd be no question about the reaction. So we've got kind of crossed results. Now, here's one of the critical parts. That in addition to that product, I'm also making HBr. Okay. So, first thing is short reaction time. And I'm going to call this, what did I call this? Product A or B? That was product A. So I just want to keep the terminology the same. All right, so this is product A, this is product B. Okay. So in a short reaction time, which product is going to be the major product? A or B? A? We agree? Okay, so in short reaction time, A is going to be the major product because it's formed from the lowest activation energy. So kinetically, it's going to be formed faster. What if I raise the temperature? And not some outrageous 300 degrees Celsius, but just I double the temperature. Which product's going to be formed most? How many people say A? If I double the temperature, A is going to be formed the fastest. You're out there all by yourself. It's okay. B is going to be formed faster. If I raise the temperature. A is still going to be formed faster. Right? If I raise the temperature, the activation energies are still the same. So it's still going to go over the lowest barrier faster. Now, I may get a little bit more B product, but A is still going to be the product that's formed faster. Okay. And again, what I'm doing is I'm not raising, I don't have the ability to raise the temperature so high that I get a 50-50 split. So no matter what I do to the temperature, A is going to be my major product. Agreed? Do we agree with that? A's got the lowest activation energy. If I change the temperature, all I'm going to do is change the percentage of B, but for the most part, A is going to still be the major product.
Wouldn't the product A go back to like the reverse reaction forming the resinous hybrid again and then going to product B if we have enough temperature.
Okay, so now let's talk about the reverse reaction, because we haven't had that in the past. That's new. So no matter what I do to the temperature, A is going to be formed fastest, but now I've got this alcohol plus HBr. So what can happen? The OH gets protonated by the H+, the water leaves, and I go back over the barrier to get back here. So this reaction is reversible. Right, if I take that OH and I add H+ to it, I would get my oxonium ion, and then my oxonium ion leaves and I go all the way back to the beginning. So my first set of activation energies that I'm concerned about is this one. We'll call this EA1 and this activation energy 1. And the same thing's true for product B. Product B is reversible back to the beginning. So now if I let the reaction go on and there's sufficient energy for me to overcome this activation energy, which would be, we'll call this the reverse, and over here, I could overcome this activation energy, which would be the reverse. I can get back to the original intermediate. So what happens when I raise the temperature? When I raise the temperature, I now can make the reverse reaction occur more. So when the temperature goes up, I get more reverse reaction. And you'd say, well, okay, it goes back to the middle, but then because the lower activation energy is still going to the right, it still goes to the right again. Okay. But if I raise the temperature high enough, maybe some B will form. Well, 2 out of 100 molecules are B. Then the other 98 go back to A. Then they go back to the middle. And then another 2 goes to the B. Now what happens if B can't get out of its well? What happens if the energy isn't enough for B to do that?
Well, depending on how long you let it go, eventually all product A will reverse back, and if 2 at a time in your example are going the other way, eventually it'll be 100%.
Or nearly 100%.
Nearly 100% B.
So eventually what will happen is most of the product will get stuck in this well. So that means that I'm going to need I'm going to need a long reaction time. So if I now change from a short reaction time to a long reaction time, now I'm going to favor B, with a sufficient temperature enough to overcome the initial activation energies. So eventually, 2 at a time, eventually nearly everything's going to end up in the B. Is going to end up as B. So I want to adjust my temperature so that it can't come out of the B well. But it can't go from A back to the middle, and it can go from the middle to B.
Would it still favor B even if it was just high enough to do the reverse reaction, because it has more activation energy to get back over that.
So it's going to have a harder time. It's going to take more energy in order to do the reverse reaction, because this activation energy is so much bigger than that one. So we're not going to get 100% of one or the other, but we're going to get we can switch major products is the critical part here. Because of this reversibility, I could get either product. I could get either A or B. Do I want A? Let's use a lower temperature. So in terms of temperature, use a lower temperature, and I'm going to favor A. Use a higher temperature, and I'm going to favor B. And those kind of go together with use a lower temperature with a short reaction time, I'm going to get A. Use a longer reaction time with a higher temperature, and I'm going to get B as the major product. And again, major product means majority product. It's not exclusive. So I now can adjust my reaction conditions to get either the A or the B product because of the way this reaction goes. But the critical part is the reversibility. Is the reversibility of the product. And that's new. We haven't seen that so far. Okay. Is everybody kind of with me here? Okay, we're going to put two terms to this. We're going to put kinetic and thermodynamic. We're going to call one product the kinetic product and one product the thermodynamic product. So what do you think the kinetic product should be? A or B? A. Why? If it's kinetic, what do you think of? It's the rate, it's the one that's formed fastest. So this one is formed the fastest. So this is going to be called the kinetic product. Wait, yes. And then this one is called the thermodynamic product. Now the thermodynamic product is the most stable product. And that fits this reaction. So the kinetic product is the one that's formed fastest. The thermodynamic product is the most stable product. Most substitute double bond. So these long reaction times, short reaction times, high temperature, low temperature, can also be called kinetic and thermodynamic conditions. Short reaction time, low temperature is going to favor kinetic. High temperature, long reaction times is going to favor thermodynamic. We can use kinetic and thermodynamic, and actually, if you wanted to go back to chapter 3 in the Top Hat textbook, you would actually see that they introduced this topic with these diagrams. Unfortunately, they introduced it how long? Way too early, right? Because I'm sure somebody was sitting there going, didn't we talk about this in chapter 3? Yeah, that person was me. So it's a nice try to introduce it that early, but by this point it's like so much other stuff has come in and crowded it out. Now it's time to remember that. Okay? So this is kinetic and thermodynamic products. And this is what we can do with an allylic carbocation that we couldn't do before. We can now write resonance structures so we can get a more stable, less stable, and that will produce a more stable and a less stable product. And there are consequences to that. The consequences are that now I can choose which is the major product by choosing my reaction conditions.
So, do get like the 1,2 products and the 1,4 products with diene?
Okay, so that's going to be the next step, is to move on to what we call 1,2 and 1,4 addition. So the reaction that I just did was simply creating an allylic carbocation from an allylic bromide. And I could do this if I put an OH reaction, OH there, and said add HBr to it. We could do a similar analysis. So now what I would hope is, now let's talk about what's called a diene. And dienes can exist in two flavors. This one, where it goes double, single, double, is conjugated. And then you have what are called isolated, where there's more than one double bond in between. So conjugated dienes are more interesting than isolated ones. Isolated dienes, it's all the reactions we talked about with dienes. You just have two double bonds to work with. A conjugated diene, though, is a different species. Because now let's take my conjugated diene, and now let me add H plus and Cl minus to the conjugated diene. Now the first question is, where should I add the H plus? In dienes, we always have this 4-carbon system. That's the two double bonds that are next to each other. We always label those 1, 2, 3, 4. And here's the rule. There's two rules. Always add the H plus to the ends of the diene system. So either add it to carbon 1 or carbon 4. The second rule is never add in the middle, which is basically just rule number 1. Okay, so I'm going to add the H plus to carbon 1. It doesn't matter because this is a symmetrical alkene, or symmetrical diene. So, okay, I bring out my double bond, and I now add my hydrogen to carbon 1. And I form a double bond to carbon 2. Does this have a resonance structure? Yes, so let's write the resonance structure. And so there's my second resonance structure. Now I'm going to take my Cl and I'm going to add my Cl to carbon 2. And I'm going to add my Cl to carbon 4. And we could have predicted what I'm going to call the 1,2 product. We could not have predicted the 1,4 product unless we went through the problem that we spent the majority of time going through, where we have to write the resonance structure. So when you have a conjugated diene and you're going to add HCl to it, or HBr, or H plus H2O, or even Br2, you're going to end up with a mixture of 1,2 and 1,4 products, which is what Lexi was asking about. So this is the natural extension then of talking about allylic sort of substitution, is let's do now what we call 1,2 and 1,4 addition. So I could ask you, I could say, which one of those two products is the thermodynamic product? Which one of those two products is the kinetic product? Which one of those two products am I going to favor if I use a short reaction time and a low temperature? Which one of those two products am I going to favor if I use a high temperature and a long reaction time? Based on what the other example that we just talked about. And actually the diagram that's in the PowerPoint notes is for this reaction, not for the one I just did. But it's okay, they're the same. It's the same principle. And your question about the 1,2, 1,4 was? You only get those with dynes, yes. And then somebody could ask the question and say, do you always get 1,2 as thermodynamic? Do you always get 1,4 as kinetic, or vice versa? And the answer is no. It's each individual reaction. Okay. So we'll finish talking about this because I want to illustrate the fact that you will get each reaction's individual, so you can't say 1,2 is this and 1,4 is always this. So we'll finish that up. I'll put the next topics, which are Diels alders. We'll finish this up on Tuesday or on Wednesday. I do have a take-home quiz for you that I will post right after class here, and it will be writing the complete mechanism of a free radical halogenation reaction. So I would like you to get some practice doing that before the exam. Here's your graded stuff from the other day. If you got to leave, you can come back. You can come and do it. Yeah, just put those over here. Put your homework problems over here on this desk. They're not
That's
in order, so
what I think we should do, just because more people would probably be able to come because, they don't have class. Just give it more time. And are you on the date? So I'm going to go through just like, now let's split it. I say in the equals
help them come to. Because I'll take that down.